The definite integral, graphical interpretation. Graphical interpretation of the definite integral. A function f of x is sometimes positive and sometimes negative. So the definite integral calculates the signed area between f of x and the x-axis over a given x interval, or the total area above the x-axis minus the total area below the x-axis. So let's say we're given this function here, and we'll call it f of x, and we're interested in calculating the definite integral on the interval from 0 to 10. We would look at the area between the function and the x-axis that is above the x-axis, so all of this area here from x value 0 to 4, and we would subtract the area that is between the function and the x-axis that is below the x-axis. So that's all of this area that exists on the x interval from 4 to 10. In other words, the area above the x-axis is signed positive, so we consider the area between the function and the x-axis that's above the x-axis positive, but the area below the x-axis is signed negative. So a definite integral from a to b of the function f of x dx is equal to the signed area of the region between the graph of f of x and the x-axis on the interval from a to b. In this first example, we want to make sure we understand the area that's represented by a definite integral. So we're going to shade the region that represents each definite integral. So here we have the integral from 0 to 2 of f of x dx. So here we're only interested in the x values from 0 to 2. We're going to shade the region between the function and the x-axis. Well, from 0 to 1, that's going to be below the x-axis, so that's going to be negative signed area. And between 1 and 2, we're going to have positive signed area between the function and the x-axis. So notice that I can't actually calculate the exact areas here. These are not perfect geometric shapes, but I can tell there's more area above the x-axis than below, so this definite integral would be a positive numerical value. Now for the second one, we have the definite integral from -1 to 3 of f of x dx. So -1 to 3 is the set of x values we're looking at. So we're going to go ahead and shade the region between the function and the x-axis between -1 and 2. I'm going to highlight that region, which forms actually a perfect geometric shape. It's a nice triangle. And that's going to be positive signed area. But we want to go all the way to 3. So the region between the function and the x-axis between 2 and 3 is below the x-axis. That would be signed negative. So if I look, there's way more area above than below the x-axis, so this overall answer is going to be positive. And we can in fact calculate it because the area forms these nice geometric shapes and we have geometry formulas to calculate the area. So we'll see an example of that soon, but just recognize here that the answer would be positive. Now, for the third example, the integral from 0 to 2 pi of f of x dx, here's our graph. If you recognize it, it's the sine function. So we're going to highlight the area between the function and the x-axis between 0 and pi first. That would be positive area. And then the area between pi and 2 pi, well, that would be negative area. That would be below the x-axis. Now here, if I tried to think about whether the area above the x-axis is bigger or smaller than the area below, recognize that it's actually the same amount of area that is above and below the x-axis. So if I were to try to add those quantities together, they're going to cancel each other out and give me 0. So even though I don't know exactly what each of these areas are, I do know that they're the same quantity, just opposite in sign, and when you add those opposite values, you're going to get the answer of 0. In this example, I actually want to calculate the integral from 0 to 3 of the function 2x minus 5 dx using the interpretation of signed area. All right, so here our function is linear, 2x minus 5, so we'll graph it, and we're only concerned with the x interval from 0 to 3. So I'm going to graph by plotting the y-intercept down here at -5, and then applying the slope, which is +2. So I'm going to go up 2 over 1, up 2 over 1, up 2 over 1. So I only graphed points between the x values 0 and 3. So I'm going to connect those points with a line since I know my function is linear. And I'm going to shade the region that is represented by this definite integral. So we have the area between the function and the x-axis. First it is below the x-axis. And then I have this little tiny portion that is above the x-axis. All right, so now we can see that the overall answer would be negative. There's more area below than above the x-axis, but we can actually calculate it because the shapes created are both triangles. So we're going to calculate the area of this triangle and the area of this triangle, remembering that when it's below the x-axis, it's considered negative, and above the x-axis, it's considered positive. So this definite integral is equal to, we'll start with the negative triangle area. So I'm just going to start by putting a negative because it's below the x-axis, and then the formula for the area of a triangle is 1/2 base times height. So here, the base of the triangle is going to be a length of 2.5. So here, this intersection point is 2.5 or 5 over 2. We could see that that's going to happen because of the slope. If we want to be more formal about it, we could set the function equal to 0 to find x-intercepts. So 2x minus 5 equals 0, 2x equals 5, so x equals 5/2 or 2.5. So our base is 2.5 or 5/2. I'm going to go with 5/2 since I already have a fraction here of 1/2. And then the height is 5. And I don't want to put -5 because I already have the negative associated with this total area from the negative in front. So I'm just going to put 5 for the height. So 1/2 base times height, that whole quantity will be negative. And then plus this little triangle here has a base of 1/2 or 0.5 and a height of 1. So plus 1/2 times 1/2 times 1. So we're using the formula for the area of a triangle 1/2 base times height. This portion right here is the area of this triangle below the x-axis, that's why it's negative. And then this portion right here is the area of the triangle above the x-axis, which should be positive. So we'll go ahead and multiply these together. We're going to get -25 over 4 plus 1 over 4. That's -24 over 4. So a total area of -6, which makes sense since there's more area below than above the x-axis. In this next example, I want to calculate the integral from -1 to 4 of the absolute value of x minus 3 dx using the interpretation of signed area. All right, so this function is an absolute value function, which is shifted to the right 3 units. So I'm going to go ahead and graph my V-shaped absolute value function shifted right 3 units. So the vertex is going to be over here at the x-intercept 3, 0. And the slope to the right of the vertex is going to be +1. And then the slope to the left is going to be -1, creating my V shape. And so I'm going to make sure and extend my graph from -1 to 4. So mine actually goes a little bit further than that. Maybe I'll erase that extra part here just to really focus on the interval from -1 to 4. So we're going to go ahead and first shade the region that this definite integral represents. It's all positive area, so the area between the function and the x-axis is all positive area above the x-axis. It's 2 different triangles, so we're going to go ahead and calculate the area of both and then add them together. So this is going to equal 1/2 base, let's see, so the total base here is 1, 2, 3, 4 units, and the height is also 1, 2, 3, 4, so base times height, and then plus the other little triangle has a base of 1 and a height of 1, so 1/2 times 1 times 1. So we're looking at 16/2 plus 1/2, so 17/2, or we can leave our answer as a decimal, 8.5. So we can see that our answer should definitely be positive. All of the area is above the x-axis. So here, the most challenging thing for students tends to be graphing. So just remember that the absolute value function looks like a v, and because the -3 is with the x, it's going to shift me to the right 3 units. The other thing we can always do, as long as we have a general idea of the shape of the graph, is plot points. So I could have substituted in x values between -1 and 4 into my absolute value function and plotted all of these coordinate points to get that shape of the graph. In this example, we want to calculate the integral from 0 to 2 of the quantity 1 plus the square root of 4 minus x squared dx using the interpretation of signed area. On this one, we want to remember that the square root of 4 minus x squared is a special graph. It's the graph of a semicircle. So as a quick review, if I have y equals the square root of r squared minus x squared, this graphs a semicircle. And the radius of the semicircle is r, and the center of the semicircle is 0, 0. So the square root of 4 minus x squared is a semicircle with radius 2. So this is a semicircle, and it has a radius of 2 and a center of 0, 0. Now there's this 1 plus on the outside, so what that does is it's going to shift my semicircle up 1 unit. So I would normally have just the semicircle. I'm going to do my best to sketch a semicircle freehand of radius 2 centered at 0, 0. So this would be just the square root of 4 minus x squared, but then we're going to take that and we're going to shift it up 1 whole unit. So what I'm going to have is I'm going to have a semicircle. Let's pretend that's a perfect semicircle or half a circle up here. And since it's shifted directly up 1 unit, the region directly underneath it, I'm going to shade in a different color, is a rectangle. So remember that we're interested in the area between the function and the x-axis. So there's this extra region when the shift up 1 happens. So what we need to do to calculate this definite integral, well, first we got to be careful because we are calculating only what's happening from x equals 0 to x equals 2. So that means I am interested in just this quarter circle right here and this rectangle right here. So I'm going to calculate the area of each of these two shapes, which I have formulas for, and add them together, and that's going to calculate this definite integral. So this definite integral is going to equal, let's calculate the rectangle first. So we have just base times height. So base 2 times height 1. So 2 times 1 plus the area of a quarter circle is 1/4 of a circle. So we're going to have 1/4 pi times the radius squared. Well, the radius of this semicircle is 2. So if we simplify this, we end up with 2, and then 2 squared is 4. 4 times 1/4 is 1, so this whole thing is just 1 pi. So 2 plus pi. And these are not like terms, so this is the best that we can do. So the definite integral looks like a quarter circle and a rectangle. So we calculate the area of those two shapes using known geometry formulas and add them together to find this definite integral. Now let's look at some properties of the definite integral. Suppose f of x and g of x are integrable over the interval from a to b and k is a constant. The definite integral from a to b of f of x plus or minus g of x dx can be broken down into the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So if it's a sum or difference, we can do each one separately. The second property says that if we have a constant, k, multiplied by a function, so a coefficient, we can pull that coefficient out of the definite integral. The third property says if I integrate from a to b over a constant, then the answer is just the constant times b minus a. This isn't really a property I encourage memorizing because if we graph it, it's very intuitive. The function y equals k is just a horizontal line. And if we're integrating over a to b, then what we're doing is we're finding the area of a rectangle with a base from a to b. Well, that distance is found by doing b minus a. So the width of the rectangle is b minus a, and the height of the rectangle is just k. So we're just multiplying base times height. Now, the fourth property says the integral from b to a of f of x dx is equal to negative the integral from a to b of f of x dx if a is less than b. So the emphasis here is on the limits of integration. And the idea is that we want the smaller number on the bottom. So if we have the bigger number on the bottom, b, and the smaller number on the top, a, we can switch them, but that will make the quantity negative. And this is something that we're going to see quite often. Number 5, the integral from a to a of f of x dx is 0. Well, that should make sense because that's calculating an amount of area. And if we're not going anywhere, if we're going from a to a, then there's 0 area there. And then number 6 says the integral from a to c of f of x dx is equal to the integral from a to b of f of x dx plus b to c of f of x dx if a is less than b is less than c. This is another one that if we draw the graph, it makes a little bit more sense than just trying to look at the notation. So let's say I have a function f of x, and we have a is less than b is less than c. This property is saying that the area from a to c, so all of this area here from a to c between the function and the x-axis, can be calculated by doing the integral from a to b, so this portion here from a to b, plus the portion here from b to c. So I think that makes a little bit more sense when you think about the graphical representation of the definite integral. Let's do a few examples using those properties. First, find the integral from 2 to 2 of the square root of x squared plus 7 dx. Well, here, if we recognize that the limits of integration are the same, we don't have to bother ourselves looking at the integrand. The answer is just 0. There is no area between 2 and 2 given any function. Let's look at another example using these properties of definite integrals. First, we're given the integral from 2 to 0 of f of x dx is equal to 2. I'm actually going to pause right away because this is a little bit weird. We don't want the lower limit of integration to be the bigger number. We want the limits to go from small on the bottom to bigger on the top. Now we had a property that says I can switch these to make it the integral from 0 to 2 of f of x dx, but that will make the answer the opposite sign. So this is going to be a negative 2 now. Then we have the integral from 2 to 4 of f of x dx is equal to negative 3. The integral from 2 to 4 of g of x dx is equal to 4, and the integral from 0 to 1 of f of x dx is equal to 1. Let's use the properties of definite integrals to evaluate the following. So here, the integral from 2 to 4 of 2f of x minus g of x dx. So let's use a property that says we can split this up to be the integral from 2 to 4 of 2 times f of x dx minus the integral from 2 to 4 of g of x dx. Being incredibly careful not to forget the differential. The differential is important. It tells us what to integrate with respect to, and it is a requirement. So now I'm going to take this 2 for my properties of definite integrals and move it to the front since it is multiplied in there. So 2 times the integral from 2 to 4 of f of x dx minus the integral from 2 to 4 of g of x dx. And we can replace each of these definite integrals with a numerical value. The integral from 2 to 4 of f of x dx, that whole thing, can be replaced with negative 3, and that's multiplied by that 2 in front, minus the integral from 2 to 4 of g of x dx, that whole thing can be replaced by 4. So we end up with 2 times negative 3 is negative 6 minus 4, an overall answer of negative 10. Now for the second definite integral, the integral from 0 to 4 of f of x dx, we are actually going to use the first two pieces of information. So the integral from 0 to 2 of f of x dx is equal to negative 2, and the integral from 2 to 4 of f of x dx is equal to negative 3. So the integral from 0 to 4, we can rewrite that as the integral from 0 to 2 of f of x dx plus the integral from 2 to 4 of f of x dx. So the total area from x equals 0 to x equals 4 can be split at the middle value 2. I can go from 0 to 2 plus 2 to 4 on the f of x function. Now, the integral from 0 to 2 of f of x dx is negative 2. So this whole first definite integral is negative 2. And the integral from 2 to 4 of f of x dx is equal to negative 3. So we have negative 2 plus negative 3. We have a total area of negative 5. Now the last part here is a little bit tricky. We want the integral from 1 to 4 of f of x dx. Now there's one piece of information we haven't used yet, and that is the integral from 0 to 1 of f of x dx is equal to 1. So we are going to need that piece of information. So I'm going to set up what we need to calculate, and then we'll talk about it. So the integral from 1 to 4 of f of x dx is going to equal the integral from 0 to 4 of f of x dx, which notice we found in this second part here. So we have all of the area from 0 to 4 of f of x dx, which is too much. We only want everything from 1 to 4. So we're going to subtract everything from 0 to 1 of f of x dx. So we have this answer from the previous part. The integral from 0 to 4 of f of x dx was negative 5. So this whole thing is negative 5 minus this part was given. The integral from 0 to 1 of f of x dx is 1. So negative 5 minus 1 is equal to negative 6. Now just to do a little graphical representation, even though this is definitely not the graph in question, but if I were to just quickly sketch a random graph of f of x, what we said in this last part here is that we had all of the area from 0 to 4. So we had all of this area from 0 to 4, but we wanted the area from 1 to 4. So we wanted all of this here. So what does that mean we have to take away or subtract is this area from 0 to 1. Now, how do I know for sure this is not the function f of x? Well, because notice that our answers for the integral from 0 to 4 of f of x dx was a negative quantity, from 1 to 4 was also a negative quantity, and my function f of x is a positive function. Everything here is above the x-axis. But this was just to help understand why we had the difference of two definite integrals to find this last definite integral quantity. Before moving on to our last part, we're going to do a bit of review from pre-calculus. A function is even if f of negative x is equal to f of x. So in other words, if we substitute every x with a negative x, and the function just eats the negatives, and we end up with just regular f of x again, we have an even function. or if graphically there is y-axis symmetry. So y-axis symmetry means that the y-axis acts like a mirror. So each point on the left side has a mirror image point on the right side. Well, this is the cosine graph, and cosine has y-axis symmetry, so it's an even function. Now, a function is odd if f of negative x is equal to negative f of x. So this time we would replace each x with a negative x, and what would happen is the function would spit out a negative. So I like to say even functions eat the negative, and odd functions spit out the negative to the front. Or if you have a graph, there is origin symmetry. And origin symmetry is when you think about rotating the graph 180 degrees about the origin 0, 0. And when you do that rotation, it looks like the graph didn't change at all. So this is the sine function, which has origin symmetry, so it's considered an odd function. We reviewed symmetry because sometimes we can use symmetry to help evaluate definite integrals. Let f of x be continuous on the symmetric interval from negative a to a. First, if f of x is an even function, and we have the integral from negative a to a of f of x dx, that is equal to 2 times the integral from 0 to a of f of x dx. So I think it's best to look at a graph. Now this is, again, the cosine function, which we know is an even function. So let's say we're analyzing this on the symmetric interval from here to here. So this is actually going to be pi over 2 to negative pi over 2. So let's say we're interested in this area here. Well, instead of calculating the entire area from negative pi over 2 to pi over 2, what we could do instead is we could calculate the area from 0 to pi over 2. And because there's a mirror image over the y-axis, this area from 0 to pi over 2 is the same as this area on the left side, and so we can just double it. So this is something that can make our calculations a lot easier, to think about the area from 0 to that a value of a symmetric interval, and then just double it. Now, the second one is an even nicer, helpful property. If f of x is an odd function, and we're calculating the definite integral from negative a to a of f of x dx, then the answer is just 0. So again, here's the sine function, and let's say we wanted the definite integral from negative pi to pi. So it has to be symmetric, same distance on the right as on the left. Now, if I highlight the region we representing there, I have all this area below the x-axis and all this area above the x-axis, and it's the same amount, it's just positive and negative, so they're going to cancel each other out and give us 0. In this last example, I want to calculate the integral from negative 2 to 2 of x cubed cosine of x squared dx. Well, here, the integrand is not something that we should be able to graph, and it's actually pretty tricky, even with some techniques that we're going to learn in the future, to find the definite integral with this particular integrand. But something that we want to notice is that the interval is symmetric from negative 2 to 2. So basically it's worth thinking about the function x cubed cosine of x squared and whether or not that's maybe an even or an odd function. So let's consider f of x is equal to x cubed cosine of x squared. Let's check whether it's an even or an odd function by replacing each x with a negative x. So we're going to have negative x cubed cosine of negative x squared. Well, a negative cubed stays negative, so this is going to be negative x cubed in the front. And then we have cosine of, well, a negative squared is a positive, so inside here we're just going to get x squared. So what happened is I replaced each x with a negative x, and I ended up with negative of the original function. I ended up with negative f of x. X cubed cosine of x squared is there, but there's a negative that's multiplied in the front. So what that tells me is that this is an odd function. So since this is an odd function over a symmetric interval, that means I can say that the answer is 0.